Okay, and we should be all good and live. Let me just open up VS Code. Okay, can I be heard? Is that? Can you hear me? Or let me just check on YouTube. Testing. Okay, good. Right, so we're all good. We can be heard. Okay, so let's pick up where we left off. Let me just clear the terminal. It wants a restart extension for C++. We'll just restart it. Shouldn't take that long. Okay, so let's finish off our question that we were starting yesterday, or we started off yesterday. I just want to check the. Yeah, okay, so the volume's good, so I don't need to worry about that. Okay. Let's go for it then. Okay. Right, so we wanted to calculate the ball after the user had done the height. So we already had the function for the double function for tower height. Calculate the ball height, but we had it all in one function. So what I'm going to do is I am going to go through let's just delete this for now. And we'll delete this for now. So we will need to return the current ball height after the variables of seconds. So we'll need a double of calculate ball height, and we'll need parameters of an integer of seconds and a double of tower height. Is that going to cause issues? Because let's do here get tower height, and then the body we will want to calculate the ball height. So in here, like we did last time, we'll need the gravity. We'll need a double of gravity, which he said was 9.8 seconds. Then one thing I did incorrectly last time was the formula. So using the formula S equals U times T plus A times U to the power of 2 divided by 2. And that's this, is it? Yes, I assume it is. So U So U is gravity. I understand that because that is okay. Using the formula of S equals U times T plus A times T to the power of 2 divided by 2. So we'll have a double of the whole distance, and we're doing gravity, i.e. the 9.8, times our integer of seconds squared. So we can just do times and then seconds times seconds, and then divide that by 2. So then we got that. Then we need the double of the ball height, which will be tower height, i.e. the double of tower height, minus the minus the fall distance. That makes sense. Speed equals velocity times time plus A times whatever A is, plus gravity being A times seconds squared. Yeah. So then if the ball is on the ground, then place it on the ground. I'm trying not to look at the answers. I'm trying to get used to it. So or trying to learn it myself, if ball height is less than 0.0, yes, less than 0.0, then we return 0.0. Otherwise, come out of the if statement and simply return ball height, which is dependent on the tower height minus the fall distance. So we've calculated the ball height. Now we want to print the ball height. I show the user where the ball is. So that would be, you would simply want to do a standard output depending on the ball height, i.e. a character output. So you do a void. Yes, you would. So I don't want to look at it. So a void print ball height, and then the ball height would be you'd need to see it would be in relation to the tower at seconds. So you would do the same again of int seconds, and then a double of tower height. So then if seconds, because we're only doing 5 at the moment, if seconds is less than or equal to 5, we then print character output at, and then I'm getting it from here, at seconds, the ball is at a height of of tower height? No, that doesn't really make sense though. And then meters, and then we'll have a line break. Else, if seconds is equal to 5, else if, there's probably a better way to do this, if seconds is equal to 5, because we need a semicolon, that's why. If seconds equal to 5, std character output at seconds the ball is on the ground. But then how are we calculating the tower height? We already done the double tower height. So we need to call the ball height, is that it? So I assume we need to call the ball height. So how would we do that? Let's have a look. So instead of, my bad, instead of tower height, it should have been ball height. And then you can just replace this with this. And then instead of seconds, we'll do the ball height. Yes, so that, yeah, there is a better way to do that. I thought so. Ball height, if ball height is greater than 0.0, else do that. Okay. So in this void function, we are simply printing the ball height and the seconds and nothing else, just like we did in the question before where we printed the result. So void functions are good for, in this situation, the logic and printing the output. Then we need to calculate and print the said ball height, which is where we need to bring all these together into one function. So calculate and print the ball height to the user. So in here, so we're going to be using a helper function, using a helper function. So it's void and then the function name, and then we're doing double height, double of a tower height, and integer of seconds. We are then creating a double of ball height, which will call the calculate ball height function, and we'll use tower height in seconds, i.e. the same exact as the arguments, i.e. the same exact parameters we passed in. And then we will print the ball height with ball height and seconds here. Okay, so avoid calculate and print ball height, and then we'll have a double of tower height and an integer of seconds. So we'll then need a double of ball height, which will, as again I'm trying not to look, which will, what will it do? The ball height will calculate the ball height. So calculate ball height, then we need to pass in the two arguments, which will be tower height, or in this case seconds, because we passed in seconds first. Helps if I spell seconds right. Seconds, and then tower height. Then we will print the ball height using seconds and ball height. Now the reason why mine is different in terms of the arguments and the parameters is because his calculate ball height, i.e. this, passed in the parameter of double tower height first, meaning when he types it in, he has to follow, the arguments have to follow the parameters in terms of order. Whereas in my scenario, in my situation, I did integers of seconds first and double tower height second, which is why I need to do seconds and tower height here. Hopefully that makes sense. So then in our main, we will get the double, we will create a double of tower height, i.e. We will be asking the user to tell us the height of the tower. Then, so we'll need to call that. We'll need to initialize it with get tower height. Then we will calculate and print the ball height for every I realize I have not given it a name. Tower height. We will then print and we will then calculate and print ball height for every second. Calculate and print ball height. But in the parameters, we will need the tower height, and we will need the integer of seconds. And since we are going to do it second by second, I'll hard code it for now. But ideally, you would want to do it dynamically. So we're going to do 0, and then we're going to do 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then as always with a main, we will return 0. So hopefully I followed along correctly, and we should now get this result. Okay, let's give it a go. We'll just clear the terminal and let's run. And then if we do 100 meters, cool. At 0, that's why, because my ball height, my else contains ball height, so it should be seconds. And then also what I want to do is I want to do a new line and line break. So what we'll do is we'll do that again. We'll run it again. We'll do tower height of 100. And at 5 is now on the ground. Cool. Hopefully that made sense. That was a lot more trickier than previous examples, particularly involving the velocity and such. But that was chapter 4 complete. Okay, so what I'll do is I will copy and paste that into my notes, because that was a more difficult question. And then that is chapter 8 of fundamental types complete. So we'll do day 9. We're on day 9, right? Let me just check. Yeah, day 9. Cool. We are on day 9. So day 9, part 1, and just finishing off fundamental data types, summary questions. Cool. Tutto bene. And today is the 6th of August. Cool. So that was fundamental data types. Now what we'll do is we will clear that. We'll close this, and then we'll get rid of all this. We'll do this. We'll return to a standard main. We'll do a return type of integer main, and then we'll just do the standard. And there's something like hello world. Hello world. And then we'll do return of 0. Cool. So now what we'll do is we'll move on to the next chapter, which is constants and strings. So I'll do 9 constants and strings. And then we'll go all the way down here. And then we'll just divide that with that. Cool. Constant variables, name constants, and then we have literals, which we've done before a bit. We got numerical, we got as if rule, we got constant expressions, constant expression variables, introducing standard string, introducing string view part 2, and then of course we always have a review. So let's get into it. Let me just get rid of that. No thanks. Okay, so constants. A constant is something that cannot be changed. Okay. A constant is something that cannot be changed. Cool. In C++, we have two types of constants. These being named constants and literal constants. And named constants are constants with an identifier. These are constants with an identifier. And then these are, a literal constant is, these are constants without an identifier. Cool. We'll cover literal constants later in the next lesson. So types of named constants. There are three ways to define. So there are three ways to define named constants. First one, constant variables. Second one, object like macros. And then third, enumerated constants. Yeah, cool. Constant variables are the most common type of named constants there are. So constant variables. For example, this x is a non-constant variable. Otherwise, x. We've seen variables so far all of the variables have been non. That is, they are able to be changed. I.e., we have integer of x. X is a non-constant, and we can change x to 5. However, there are many cases where it's useful to define and not be changed. Yes. For example, gravity, like we did in the last. No, I don't want to save that. I'm going to save this one. That we did in the summary question. So, declaring a constant variable. So, to declare a constant variable, we use the const keyword, such as const double gravity, and then we will initialize it with 9.8. Or we could do int const side in number of sides in a square, and then that would obviously be 4. I agree with him here. I think I prefer this over this, because you're setting the constant, then you're providing the identifier, then you're providing the, sorry, not identifier, the type, then you're doing the identifier, and then you're assigning it. Whereas this, you're doing the type, you're making it a constant, and then you're providing the identifier and then assigning it, and sorry, initializing it. Yeah, that's the way I prefer it. But if you prefer int const, then that's fine. I prefer this way. Okay. Yeah, best practice, more conventional. Key insight. So when we define the type is gravity, yes, the type. The type is gravity, and the type of gravity is a constant double. Yeah. Constant variables must be initialized. They constant variables must always be initialized. Yes, as we saw there. Yeah. So that won't work and that won't work. That makes sense because we've declared the constant, we've identified the type, the data type, we've set the identifier, but we haven't initialized it. And we can't then make it equal to something else. So in this example, we have we've included the input-output stream library. We've set the main return type to integer. A standard character output, enter your age. The user then enters their age, and then we enter their age. Then we have const age being age, i.e. we are setting a constant variable, we're setting the data type, we're setting the identifier, and then we're initializing it with the age they enter. So then age then equals 5. That is okay because our age is not a constant variable. Whereas this is not okay because const age is a constant. And as we learned just a few seconds ago, constants cannot be changed. So that will produce an error. Let's just show that just for example. So we include IOStream, a return type of integer. For our main function, we'll do a standard character output of enter your age. Then we will do a int of age, i.e. a variable of age. Then we will allow the user to enter said age with age. Then we can we will set const integer, the data type, then the age, and no, const age. Then we will set that to age. Then we will set the variable, i.e. the non-constant age, to whatever, we'll do 5. Then we will set a const age equal to 6, and then we'll obviously, as always, return 0. But as you can see here, we have the error expression must be a modifiable value. And as you can see, our const age is not. So before we even run, we're getting an error. Yeah, hopefully that makes sense. The initializer of a const variable cannot be a constant value, a non-constant value. Yes. So we'll just get rid of that. For now, we'll just return 0. Okay, cool. How are we looking? Still looking good? Yeah. Cool. Naming your const variables. There are a number of different naming conventions for constant variables. Programmers who transition from C often prefer upper name constant variables. More common in C++ is intercapped with a K preference. I assume K means constant with a K. However, constant variables act like normal variables, except they cannot be assigned to. There is no reason for special naming convention. For this reason, they prefer camel case. I'm going to use this for now because I prefer it. Like for example, when we were doing the preprocessors and we were doing define, I'm going to actually, to be fair, if you have const data type identifier initializer, assuming and it's a variable, maybe you can use camel case, i.e. this. So maybe I'll leave the define, i.e. the preprocessors for the libraries, etc. For that. And I'll just keep it as camel case. I don't like that already. I've never used K prefix, but I just don't like it from the beginning. So actually I'm going to get rid of that. I'm not going to make a note. I'm just going to name my constant variables with camel case. But if you'd like to use Earth gravity, use Earth gravity. If you like to use Earth K, use Earth K. So const function parameters. Function parameters can be made with const via a keyword. So void print const x. 5 will be used as the initializer for x. 6 will be, okay. Parameters. So function parameters can be made constant via the const keyword. So we've got a void return type, printing an integer, and then the const, we have a constant, then we have a data type, then we have the identifier. And we're printing out x. So 5 will be used as the initializer for x. Note that we didn't provide an explicit initializer for our const parameter. The value of the argument in the function call will be used for the initializer of x. Okay, so it seems that using const in the function parameter is unnecessary and can, if anything, just add clutter to your functions. The proper use of const is important. I still want to use that, and then we'll just make a note of that. Const return values. A function return value may also be a const. So a function return value, so as can also be a const, as well as other data types. Such as this. So const int get value return 5, and then we have an integer of main, and then we have standard character output of get value, and then a line break, and return 0. For fundamental types, the const qualifier on a return type is simply ignored. Your compiler may generate a warning. For other types, which we'll cover later, there is typically little point of returning const objects by value, because they are temporary copies that will be destroyed anyway, i.e. destroyed when we reach here. Returning a const can also impede certain types of compiler operations, which can cause lower performance. So quindi the best practice is to not use const return types. Okay, crystal clear. Why variables should be made constant. If a variable can make constant, it should be. It reduces the chance of bugs, improves more opportunities to optimize your program. Most importantly, it reduces the overall complexity because you obviously cannot change it. Every moving part in the system increases complexity. Non-constant are moving parts, or constants are not. That makes sense to me. Why variables should be made constants. and then we'll just copy and paste that because I feel like I don't need to write that out. I understand that. And writing out will just take even more time. So, object like macros with substitution text. In lesson 2.1, we discussed object like macros, i.e. this. When the preprocessor of the file contain the code, it will replace my name, Alex, with Alex. Yeah. Note that my name is a name, and the substitution text is a constant value. So object like macros with substitution are also named constants. So that is a constant. Then we're providing the identifier. Then we're providing the initializer. So I guess you could think of that as the constant and the data type. This is then the identifier. This is then the initializer. Okay. Prefer constant variables to preprocessor macros. So why not use preprocessor macros for everything? There are at least three major problems. Macros. There are three major issues with using preprocessor macros or named constants. First, the biggest issue is that macros don't follow normal C++ scoping rules. Once a macro is defined, i.e. once defined, all subsequent occurrences of the macro's name will be replaced. If the name is used somewhere else, you'll get a macro substitution where you didn't want it. So for example here, we define gravity, and then we have a double of gravity, which means that gravity will always be 9.8, but we want to print 3.17. That makes sense. Two, it is often harder to debug code using macros. Although your source code will have the macro name, the compiler and the debugger will never see the macro because it's always been replaced before. Okay. Many debuggers are unable to inspect the macro value and often have limited capabilities. Okay. Third, macro substitution behaves differently than everything else. Inadvertent mistakes can be difficult, can be easily made as a result. So it is best practice not to use macros when defining constants. With substitution text. Okay, using constant variables through multiple programs. In many applications, a given name constant needs to be used throughout the program, not in just one file. This can include physics or maths constants. And it looks like we'll cover that later. Nomenclature, type qualifiers. A type qualifier, sometimes called a qualifier for short, is a keyword, and const is a type qualifier. Okay, let's move on to the next lesson then. Literals. How are we looking on the stream? We're still good? Yeah, okay, cool. We're still good. Literals. Literals values are inserted directly into the code. E.g. Return 5, return 5, bool, my name is Alex, with the initializer of true. Data type of double, initializer of D, and then 3.14, and then standard character output, hello world, battle chestnut, with a line break. Yeah. Literals are sometimes called literal constant because they meaning they cannot be redefined. Yes. The type of literal. Just like objects have types, all literals have a type. The type of literal is deduced from its literal value. For example, a literal that is a whole number is deduced to be a type. We'll do another subsection. So, literal value of integer, boolean, floating point, character, C* string. What is the best way to do this? Maybe if I actually copy and paste it, and I can format it, literal value. And then if we do that, yeah, maybe that's the best way. Bool value, true, false. Floating point value, Yeah, maybe that's the best way to do it. We don't actually need that actually. So we don't actually need the note section. And then we can make more space here. Yeah, that's probably the best way I can think of doing it. Yeah, it doesn't have to look perfect. Literal suffixes. If the default type of literal is not as desired, you can change the type by adding a suffix, a something afterwards. Here are the most common type of suffixes. Remember, suffix is after, prefix is before. So data type, integral, floating. So we can have a suffix of u for unassigned, integral of L, more in a moment, yeah. Most, except for F, and F is a floating point. Okay. Is that because when dealing with integers, if we have unassigned, we literally just put unassigned. So we don't, we would do unassigned int and then the variable name, the identifier rather, then we would do the initialization. So what I'm going to do is I'm going to copy and paste that. I'm going to take a screenshot of that as well. For future reference. So let's just do that. And this should be a bit easier. Almost done. Long double, standard string, and string view. Okay. In most cases, the suffix isn't even needed. As we discussed previously with integers, meaning we usually can do the identifier or the literals earlier. Suffix casing, they're not they are not case sensitive. Prefer L. Okay. Integral literals. You generally won't need to use suffixes for integral literals, but here are some examples. Let's go through it anyway. So that's that's an integer by default. L would be a long signed integer, and then U would be unassigned integer. In most cases, it's fine not to non-suffix integer literals, even when initializing non-int types. So we have a int a, we have a data type of integer, initializer a, and then a data type of integer, an identifier of a, and initializer of 5. Then we have unassigned int, or a data type. We then have identifier of b, and then initializer of 6. Then we have a long integer data type with the identifier c and initializing it with 7. In such cases, yeah, I understand that. Floating point literals. By default, floating point literals have a double. So here we have standard character output of 5. No suffix of this type is double by default. So what does that actually produce then? So again, we'll do include IOStream. We'll do a return type of integer for the main. We'll then do standard character output of 5. And then we'll do a line break. And then we'll do standard character output of 5.0 float. And then we'll do a line break here. And then we'll do a return of 0. So what is the difference in that? So we'll do include IOStream, return type of integer for our main function. Then we'll do standard character output of 5. Then we'll do a line break, not n. Then we'll do a standard character output of 5.0 with a float. And then we'll do a line break and return 0. I don't want to break, no. And then 5. Okay, so it still produces 5. New programmers are often confused about why the following causes them. So we got a data type of float with a identifier of f, and we are initializing it with 4.1. Is a double literal, not a float literal. Because 4.1 has no suffix, the literal type double, the literal has a type of double, not a float. So that means in this scenario, so the first 5.0 has a literal type of double, whereas using the suffix of f, the second 5.0 will have a literal type of float. Okay. So we got a data type of float. We have an initializer of, we have a data type of float. We have an identifier of f. Then we initialize it with 4.1 f suffix, i.e. float is now a float, and a double, we have a data type of double we have a identifier of D, and we have an initializer of 4.1. How are we looking? I am just going to take a break here for scientific notation for floating point literals. Okay, we'll take a break, and I'll be back in just a second. Cool. Okay, and we're back, and we still volume all good? Yeah, good. Okay. Right. Oh, we're scientific notation for floating point literals. Yeah, so to make a float, actually a float and not a double, we need to add the suffix of f. So there are two different ways to write floating point literals. Standard notation, one, no, first, um, okay, I understand. First, write it with a decimal point, i.e. such as these. Second is to use e, like we learned in the previous stream. Second, use e to represent the exponent. Like we covered previously. Yeah, that's fine. String literals. In programming, a string is a sequence of characters. String literals. A string is a collection of characters. Hello world is a string literal. Yes. String literals are placed between double quotes to identify them as strings, whereas chars are single quotes. Because strings are commonly used in most programming languages include fundamental string data type. But this doesn't seem to be the case for C. There are two non-obvious things about. There are two things to consider about C style strings. The first is all C style. I'm typing this one out because I actually do not know about this. And I find that if I type or write something out, it's a lot easier to stick in my brain. A C style string literal, literal have implicit null terminators, i.e. 0. Second, unlike other literals, which are values, not objects, C-style literals are const objects, okay, that are created at the start of the program and are guaranteed to exist for the entirety of the program. So does that mean that they're not destroyed when, for example, they're in a function and it's the end of the body? Perhaps. Oh, no. Unlike C-string literals, literals create temporary objects. These temporary objects must be used immediately as they are destroyed at the end of the... No, sorry, I was wrong. But that's okay. Being wrong is fine as long as you learn from it. Magic numbers. Interesting. Magic numbers. Not Magic Mike, magic numbers. Magic numbers. Okay. A magic number is a literal, usually a number that either has an unclear meaning or may need to be changed later. So magic number is a literal, usually a number that either has an unclear meaning or may need to be changed later. So a variable, so similar to a variable. Here are two examples. So we have a constant, we have a data type of integer, we have an identifier of max students per school, and then we have the initializer of num class rooms times 30, and then we set max to be 30. What do the literals 30 mean in this context? In the former, you can probably guess that the number of students per class. but not immediately obvious. Who knows? We'll have to take a look at what the function does. In complex programs, it can be difficult to infer what the literal represents, unless there is a comment to explain it. Using magic numbers is generally considered bad practice because in addition to not providing context as to what they're used for, they pose problems if the value needs to be changed. Okay, to do so, we need to update. Okay. Fortunately, both like the content. Okay, so it seems it's best practice to avoid using magic numbers. So surely you would just use a variable, no? That's what I thought. Practice to avoid using in your code. Okay, next lesson. Numeral systems. Numeral systems. I'll just create a subsection of that. Numeral systems. Okay, in everyday life, we count using decimals. By default, okay. By default, numbers in C++ programs are assumed to be decimals, i.e. don't need to copy and paste, we can just type that out quicker probably. Interesting. In binary, there are only 2 digits, ones and zeros. Yes. So it is called base 2. Base 2. We count like this. Yeah. Okay. Bases, maybe? Bases. In binary. So binary is made up of 1 and 0. This is therefore considered as base 2. To make them easier to read, we what do? We group them up into 4 digits such as 1100100. Decimal is made up of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we call this base because there are 10 digits, so it's base 10. This is therefore considered base 10. Cool. Hexadecimal, hexadecimal is base 16, and then octal, like an octopus, is base 8. Base 8. So octal is made up of 0, 1, 2, 3, 4, 5, 6, 7. This is therefore considered base. Yeah, that is annoying. Stop that. In octal we count in octal we count like that. Okay. To use an octal literal, we prefix the literal with a 0, i.e. Int x 012. Okay. Hexadecimal is made up of this type of structure. And is therefore considered base 16. To use the hexadecimal literal, we use the prefix to use hexameter prefix. We prefix the literal with 0x. Okay. I.e. int x 0x f. This will print 15. Yes, I will definitely copy, make a note of that. If I copied and pasted it, would it print exactly like that? Or paste exactly like that? No, it wouldn't. What if I extended it? Yes, it would. Okay, so it's fine like that. Using hexadecimal to represent binary. So, using hexadecimal to represent binary. Sorry about that. Just had to go and do something. Right. Let's continue. Okay. Where were we? Where were we? Using hexadecimal to represent binary. Yeah, because 16 goes into 4. Yeah, we can copy and paste that. Now that we know it'll look fine. Maybe a screenshot would be better for that. Oh, whoops. No, let's do that. And then what if we did that? I can sort that out later. Consider 32-bit integer with a binary value of that. Because the length and repetition of digits, that's not easy to read. In hexadecimal, it would be, for example, this binary number, this binary value, not a number, value of can be represented with the hexadecimal value of that, which is more concise. For this reason, hexadecimal values are often used to represent memory addresses. Okay. Which is a lot more easier to read than the binary value. For this reason, hexadecimals are used to represent memory addresses or raw data in memory. I'm spelling memory correctly. Okay. Right. Binary literals. Binary literals, prior to this, there was no support. However, hexadecimal literals provide us with useful program. And to make a hexadecimal, we use 0x and then whatever we want. 0xf, yes. Okay. Digit separators. Because long literals are hard to read. Yes, so within 4 digital separators. Digital separators. Separators. No, I've copied that, haven't I? Because stop doing that. That's annoying. That is so annoying. Note, we do not use, but rather use for the separator. Just a note to myself. And we do it in, it needs to stop. Yeah, it's much easier to read. Outputting values in decimal, octal, or hexadecimal. By default, it produces that. Okay. Outputting values in decimal or hex. So we know that by default it produces decimal. So by default, C++ produces output in decimal to output into the desired value, we can use standard character output decimal for decimal, standard oct for octal, and then standard hex. Standard hex for hexadecimal. That makes sense to me. Yeah, outputting values in binary. Outputting values in binary is a little harder, but we can use bit set. So to output values in binary, we can use bit set, but we must use the library, C++ default library of bit set for this to happen. For this to happen. Cool. Which looks something like this. So I'll do it in main first, just to be able to actually see what happens. So we'll include bit set, then we'll include IO stream, then we'll do an integer return type for our main value, for our main function, and then we'll do standard bit set, then we'll do that 8 then we'll do that 8 and then bin 1 bin 1 and then copy and paste that. Then we'll do standard bit set eight. Why is that not 8? Bin 2, the hexadecimal value of 0xC5, and then we'll do standard character output of bin 1 and then a line break, and then we'll do standard character output std bin set bin set. Are we still alive? Yeah, we're still alive. Okay, good. Sorry, I thought I messed up then. Sorry about that. I was just looking at something else. So standard character output, std, bit set, not bin set. Bit set, and then 4. Well, with the type of 4, This is going to have to take a lot of getting used to. And then a line break, and then return 0. What was the we did this in the static cast, didn't we? So what was cast? New type. So type. So the type. I thought it was a type, but I just wanted to make sure I was correct. So the type. So so the type. That is quite a lot of getting used to. So let's actually see what that prints first, rather than just carrying on obliviously. So we'll run that. And we get that. Oh, I don't get twice the value. Is it because I've done something wrong? Bit set, yeah. Bit set 8. Standard character output bin 1. Bin 2, that's why. Because I have not done bin 2. Then we do a line break. And now we should get 3 values. Or 3 lines, yeah. So 4 bits. Okay. So within the crocodiles is the number of bits. The values within are the bits, i.e. 4 bits or 8 bits, etc., etc. This makes sense because a binary is just made up of bits. A binary value is just a bit. I think I'll leave that for now. I'm not as advanced. So using the table above, what is 32 in binary and hexadecimal? So using the table above, so using the table above, what is 32 in binary and hexadecimal? Right. So binary in hexadecimal would be so you can only go up to F in hexadecimal. So that means it would be 20? No, sorry. 10, 11, 12. So 32 would be 20. Let's just make a note of this. Question. What is 32 in hexadecimal and binary? So hexadecimal only goes hexadecimal goes from 0 to 9, then A to F. So we have 0, so we got 9 being 9, and 10 is A. That's why 1F. So 32, so 32 would be, 32 in hexadecimal would be 20, I think. And then 20 in binary would be, sorry, 30 in binary would be 1, 1, 1, 1, 1, 0. 1, 2, 3, 4. 1, 2, 3, 4. Like that. 1, 1, 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it'd be that. So how many ones? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I think 32 would be 1, 1, 1, 1, 1, 0. Oh, sorry, no, it would be, because we count backwards. We write it out left to right, but we read it right to left. So 32 in hexadecimal, I think, would be 20. And then in binary would be 0, 1, 1, 1, 1, 1. Let's have a look and see if I'm right. Okay, so I'm right on the hexadecimal, but wrong on the binary. Okay, and that is because why is that? Because why did I've essentially got them flipped the other way around. So 0, 1, 1, 0, 1, 1. So when, okay. So no, 32 is actually 1, and then it'll be 1, 2, 3, 4, 5 zeros, right? 5 zeros, yeah. So 1, 1, 3, 4, 5. 1, 2, 3, 4, 5. No, it would be 5. I don't need an extra 0. So this is because, and I realize this now, this is because this is because in binary, we when we have completed a value full of ones, the an additional digit is added to the value, and the first digit, the first value, must always be 1. And so all the previous ones within the value must value become zeros. For example, 31 is 1, 2, 3, 4, 5. So therefore, with all the values being being 1, we then increase the number of digits, and therefore 32 becomes 6 digits and looks like this: 1, 2, 3, 4, 5. So that means 33 would be 1, 0, 0, 0, 0, 1. Is that the correct? Yes, so 33 in binary would be 1, then 4 zeros. Correct? Is 33 in binary 1, 1, 2, 3, 4. Yes. Okay, so that's right. And then 34 would be that? No. No, so you want to, okay. Then 34 would be then 30, I know this is getting repetitive, but 35 would be 1, 0, 0, 1, 0, 0, right? So 35 would be 1, 0, 0, 1. Okay. Perhaps I need to study a bit more on binary and the formula of how to do it. it's all about remainders and modulus. And that it breaks down into the various bits because binary is bit integers. Okay, I will have a look at that off stream and get used to that more often. Okay, I think for now we'll take a small little break. Are we on a? Are we? Oh no, we finished this bit. As if rules and compile time optimization. So how are we looking on chapter 5? Okay, so we got quite a lot. So we probably won't finish chapter 5 today. But what I want to do is I want to take a quick break here, and we'll come back and we'll do as if rules to compile time optimization. All right, see you in a minute. Okay, we still good on the stream? Just to double check. How are we looking on the audio? Yeah, we're good. Okay, let's continue. Okay. Right. So where were we? we were just about to start as if rule. And I will learn binaries off and hexadecimals off camera. Let me just make a note of that because I think that is useful to learn and actually get it stuck in my head rather than just copy and paste and make notes. It was hexadecimal, binary, and what was the other one? Octal. Okay. At the as-if rule and compile time optimization. Okay. Copy and paste that. Okay, in programming, optimization is the process of modifying software to make it work more efficiently. Makes sense. Optimization can have a huge impact on overall performance. Some types of optimization are typically done by hand. A programmer called a profiler can see how long various types of the program take to run and then obviously optimize it. Yeah. Other kinds of optimization are performed automatically. Another programmer called an optimizer, low level, looking for ways to improvement. For example, if you write this, the optimizer might write it as that. Yeah. For integral values, they produce the same result, but one may be faster. A programmer would probably not know the most performant choice, but the optimizer would, for a given system, would. Most C++ compilers are optimizing, meaning they want to run as fast as possible. Okay. Because optimization involves trade-off, compilers typically support multiple optimization levels that determine how aggressively to do so. Most compilers default to no optimization if you're using command line compiler. Yeah, you'll need to enable optimization yourself. Okay, if you're using an IDE, the IDE will automatically configure release builds to enable to enable optimization and debug builds to disabled optimization. The as-if rule. In C++ compilers, compilers are giving a lot of leeway. The as-if rule says that the compiler can modify a program however it likes in order to produce the optimized code, so long as the modifications do not affect the behavior. Modern compilers employ a variety of different techniques in order to optimize the program. An optimization opportunity. Consider the following short program. So we got include the library of input output stream. We got a return type of integer. We got a function identifier of main. We then have the function. We then have an integer of x of 3 plus 4. We have a standard character output of x, and then a new line break. And we produce 7. However, there is an interesting optimization possibility hidden within. If the program were compiled exactly as it was written, the compiler would generate and execute 3 plus 4 in the runtime. If the program were a million times. Because the result never changes, this would be wasteful. Compile time evaluation. This is cool, okay. So, key insight. Compile time evaluations allow the compiler to do work at compile time that would otherwise be run at runtime. Because expressions no longer need to be evaluated at runtime, representing executables is file. Okay. So they run at compile time evaluations allows a compile. Yes, so they run at compile rather than at run, because you compile the code, then you run the code, right? That's the order. Let me just double check. In C++, do you compile first and then run, or the other way round? Oh yeah, compile and link, of course. Yeah, so you compile compilation first, and then you run it through the compiler. Okay. For illustrative purposes in this lesson, we'll look at some optimization techniques. Yeah, okay. Constant folding. Constant folding. One of the original forms of compile time evaluation is called constant folding. Okay. It's called constant folding. Constant folding is, so this is an optimization technique where the compiler replaces expressions that have literal operands with the result of the expression. So we just change, yeah, we put in 7 rather than 3 plus 4, meaning we get rid of the operands and just do 7. Constant folding can be applied to sub-expressions when the full expression is executed at runtime. In the example 3, the compiler can up this to 7. Yeah, okay, that makes sense. Constant propagation. Propagation. Because if I don't include an example and I come back to this, I'll be like, what is he talking about? And what I want to do there is I want to have the example here, so that when I come back, when I go here, I can have a look and see, oh, that's where you get 7 from. Okay, constant propagation. The following program allows for another optimization. When x is initialized as 7, it will be stored in the memory and allocated to x. On the next line, the program will go out of memory, again to fetch 7. This requires 2 memory operations. Constant propagation is optimization technique where the compiler replaces variables known to have been constant values with their values. Using constant propagation, the compiler will realize that x always has the value of 7 and will replace x with 7. This would be the equivalent of doing the following. This removes the need for program to go out to memory and collect. Okay. Isn't that what we just do anyway? Constant propagation may produce results that can... In this example, constant propagation would transform x, y to... Hang a minute. So I understand about the next line and going out of memory and essentially doing 7. But isn't that just the same? Isn't that just the same as doing the 3 plus 4? Because you're still going out of the standard character output, out of the memory, into another memory. No? Dead code elimination. Dead code elimination elimination. Dead code elimination is the optimization technique where the compiler removes code that may be executed but has no effect on the program behavior. So we have a data type of integer, a identifier of x, and a initialize 7. In this program, variable is defined as x and initialized, yet, but is never used anywhere, so the program has no effect on the behavior. dead code elimination would be removing X. Okay, yes, that makes sense. So when a variable is not used, this is actually, if you use Swift, or sorry, if you use Xcode in Swift and you create a variable, often you'll get a little white, or no, a yellow tab. Say your code is here, you get like a yellow tab here saying this is never used, replace it with something like, so say you have int x of 7, although that wouldn't be the syntax in Swift. You would get a little warning sign here saying it's not used. Either get rid of it or you replace it with this. But in this scenario, we can just get rid of it entirely and perform or change it to a literal of 7, just for other languages if you're interested in using them. Is when a variable is defined but not ever used. So we can remove it. For example, the following code. Int x 7 is never used, so we can replace it with a literal. And then I'll copy this to this. Yeah, cool. Hopefully that makes sense. When the variable is removed, it's optimized out. And therefore we only have 2 statements in our function. Const variables are easy to optimize. So we learned a few hours ago now that we can use const variables and they do not change. Const variables are easier to optimize. In some cases, there are simple things that we can do to compile more effectively. Constant propagation can be challenging for the compiler. In this section, constant propagation, we offer the example. So data type of integer, identifier of x, and then the initializer of 7. And we're calling x here. Since x is defined as a non-constant, in order to apply this optimization, the compiler must realize the value of x actually doesn't change, even though it could. Whether the compiler is capable of doing so, it depends on the routine. We can help the compiler by using constant variables wherever possible. Okay, so constant propagation can be challenging for the compiler. So if we use constant values, it does not need to go to the memory address and fetch said variable. Right? Is that on my... Am I saying that right? Yeah. Value optimize. So this code will go from this to this, and then it'll just be a const now. Because x is now a const, the compiler has, because x is now a const, the compiler has guaranteed that x will never change. This makes it more likely the compiler will apply constant propagation and then optimize the variable entirely. That makes sense to me. Optimization programs can be hard, can make programs harder to debug. Nomenclature, compile time constants versus runtime constants. So constants in C++ are sometimes divided into two informal categories. A compile time constant is a constant whose value is known at compile time. That makes sense. Examples include literals, constant objects whose initializers are compile time constants. A runtime constant is a constant whose determined at runtime. Makes sense. Constant function parameters, constant objects whose initializers are non-constants or runtime constants. That makes sense. How are we looking? We still good? Yeah, we're still good. Okay. For example, right. So we have the library of IOStream. We have a return type of integer on our function 5. We return 5, i.e. a literal, which would be a compile time constant. Then we have a return type of integer for our variable, for a function of pass. And we're passing in the parameter of a constant data type of integer and a identifier of x, and we're again returning x. So our return type of integer for main, and then we're using maybe unused. We did maybe unused quite a few streams ago, and essentially maybe unused is sort of like an optional, i.e. is telling our IDE at compile time, this may or may not be used. So don't freak out if it's not used. I think that was introduced in either C++ 17 or C++ 14, one of the two. But feel free to go back and check a previous stream where we discussed that. One of the first streams, maybe day 1 or day 2. I doubt it'll be day 3. But if you want to go, I'd highly suggest you go and check that out. So, the following are non-constants, yes. The following are compile constants. The following are runtime constants. So I understand why those are non-constants. These are compiled constants because uh, they are constant objects whose initialize they are literals and they're constants. And yes. And this is a compiled time because it's a constant object whose initializers, i.e., this, um, is a compiled time constant. Yes. Then we have runtime constants, um, um, which can either be constant function parameters, such as this, or constant objects whose initializers are non-constants or runtime constants. So this is a non-constant, i.e. a non-constant, i.e. this one here. Then we have this referring to E, which is basically the same thing. Then we have G, which is referring to a function of 5, which is a constant object, because we don't know it until runtime. Then we have H, which calls pass, which has a constant parameter, which means we need to pass it in the argument, which is why we make that a runtime constant. Yes. So I'll make my own notes for this. This is a literal, so therefore calling it will be a runtime constant. X is a runtime constant because the what? The function parameter is a constant. This is because it is a literal. This is because it is a literal. This is because B is a literal. No, sorry, that's wrong. Is a compile time constant. Yeah, I don't think I need to add to that. A is a non-const. So it is a runtime. E is a runtime constant because E refers to A and A is a non-constant. G refers to 5 and 5 has a return. Yeah. So actually that's wrong. I'll take that out. Yeah, I don't want to deceive you or deceive myself in the future when I come back to it. although you will encounter these terms out in the wild, the definitions are not that useful. Some runtime constants can be evaluated at compile time under the as if. Compile time constants cannot be using compile time features. I'll just copy and paste that because that may be or may not be useful in the future. Okay, constant expressions. Making good progress, I think, today. I think, so what's the time now? We're just gone 12:30. I think we'll take a quick break here and we'll come back maybe for another half an hour, 45 minutes. Let's see. All right, I'll be back in a minute. Okay, and we're back. Again, just want to double check my audio is all good. Just give me a sec. Yeah, we're all good. Okay, cool. Um, okay. I think what we'll do is we'll go until about 1 o'clock. Let me just turn that down. I don't want any feedback on my audio. Yeah, so they're not reverberating. Okay, so we'll go until about 1, and then we'll see where we are. Sounds like a plan. Okay, constant expressions. Expressions. So this is an example of an expression. By default, expressions evaluate at runtime. So we know that from previous lessons and expressions by default are ran at runtime. In some cases they must do so. For example, character input, and character output. Because input and output can't be conformed at compile time, expressions above are required to evaluate at runtime. That makes sense to me. In the prior lesson, as-if rules, we discussed the as-if rule and how the compiler can optimize programs. Yes, under the as-if rule, the compiler may choose to evaluate whether expressions run at compile or runtime. Makes sense? So through the as-if rule, the compiler can optimize So for example, this may evaluate at runtime or compile time. The expression x plus y would normally evaluate at runtime because the value of x are not the value of x are known at compile time. The compiler may opt to perform compile time evaluation instead of initialize x, with the compile time calculated at 4.6. So this is because so we have this, which is a literal, which means it would be at compile time. We have this is a literal, so it would be at compile time. However, x and y are constant objects, so it may run. Okay, yeah, so it may run at runtime or compile time. Yeah, that does make sense because of this. Again, if you're struggling or unsure, as I was there, perhaps it's best to go back to this just to keep reminding yourself as to whether it runs at compile time or it will be at runtime. Okay, so let's copy that. Again, if you're struggling again, don't worry. The C++ learning curve is very, very steep. You can read all about it elsewhere on the internet. In other cases, the C++ language requires an expression that can be evaluated before compile time. For example, constant expression variables require an initializer that can be evaluated at compile time. Okay, now we're getting into more tricky stuff. Just a second. Yeah, cool. So in a few other cases, the C++ language requires an expression that can be evaluated at compile time. For example, const expression variables require an initializer that can be evaluated. Initializer is the value we give. Yeah, that can be evaluated at compile time. So here we have a runtime, we have a return type of integer, we have a function of main, we have a constant expression, and then we have a data type, we have a identifier, and then we have a initializer of express. Because variable x is a constant expression, xpr must be evaluated at compile time. So constant expressions are evaluated at compile time. In cases where constant expression is required but not provided, the compiler will halt the error. We'll discuss that later. So does that mean const expressions are always ran or no? Always evaluated at compile possibly. That would be a question for me. If I remember, I will come back to. But we'll discuss constant variables later. The benefits of compile time programming. So how are we looking on this? Quite a bit. I don't think we'll be done by 1 o'clock, but yeah, let's have a look. Or let's see where we are at 1 o'clock. Okay, because then that'll be about 3 hours. So, the benefits of compile time programming. While the as-if rule is great for improving performance, it leaves us relying on a sophisticated compiler. This means if any section of the code we want to compile may or may not do so. The same code compiled on a different program, on a different platform. I'm not finding it boring, it's just whenever I learn something, my brain needs to compute it and I always seem to yawn, so don't worry. The same code compiled on a different platform may produce a different result. Because the as-if rule is applied invisibly, we get no feedback. Code we desire to be evaluated at compile may not be done so. To improve this situation, C++ language provides us ways to be explicit about our code when we want compile time. The language features is called compile time programming. So the C++ language provides us with the ability to be explicit about this. These features can help improve the software in a number of areas: performance, versatility, predictability, quality, quantity. This allows us to improve the software in a number of of areas. Areas such as, and then I won't bother going over that. The main ones are the performance, versatility, predictability, quality, quantity. And if I need more insight, I will just read this. And feel free to pause the video or rewind and then just read it yourself. So, performance, versatility, predictability, quality, two qualities. Quality, yeah, it's not quantity and quality, it's quality. To summarize, compile time evaluation allows us to write programs that are both more performant and of high quality, more secure and less buggy. So while compile time evaluation does add additional complexity to language, the benefits are substantial. The following C++ features are the most foundational to compile time programming. So the following C++ features are the most foundational to compile time programming. Const expression variables, const expression functions, templates, static assert. All of these, I believe, are in the keywords of C++, which we did in one of the first streams, which are all of these here. So we got a const expression here. We can have functions or variables. Templates, maybe that's not keyword. Oh, it is, template. And then static assert. And obviously we did static, last stream we did static cast, which is when we want to convert a integral type, we want to convert a double to an integer, or an integer to a double, or a character to an integer using ASCII, or we want to convert something else. And remember, static cast is static cast and then new type, and then we want to pass in the expression. Yeah, cool. So now we go down here and we will, let's write it out by hand. So const capital, const, is it always capital? No, I'd rather not do it capital. Const, we're not actually writing code, so why not? Variables, const functions, templates, and then finally our static assert. All these functions have one thing in common: they make use of constant expressions. Cool. Time is another 5 minutes. So, constant expressions. Perhaps surprisingly, the C++ barely mentions compile time. Instead, it defines a constant expression, which is an expression that must be evaluatable at compile time, along with rules on how to determine how the compiler should handle these expressions. Constant expressions are the backbone of the compile time evaluation in C++. I feel this is an important note to make. In previous lesson, we defined an expression as a non-empty sequence of literals, variables, operators, and functions calls. How are we looking? Yeah, we're still good. So we know from previous experience, let's call it experience. We know from previously an expression is defined as a non-empty sequence of literals, variables, operators, and functions calls, because in our main function, in our typically return type of integer main, we run a sequence, i.e. the sequence of code. So we go from top to bottom and we run all of that, which is why it is a non-empty sequence of literals, variables, because we can call variables, operators, and function calls. Yes. A constant expression is a non-empty sequence of literals, constant, variables, operators, and function calls, all of which must be evaluated at compile time. The key difference is that in a constant expression, each part of the expression must be evaluatable at compile time. Okay. In a constant expression, each part of the expression must be evaluated. Okay, so we did that. Let me just write that myself. With a constant expression, and I want to actually change that to that. In a constant expression, in a constant expression, each part of the said expression must be evaluated at compile time. An expression that is a non-constant expression is often called a non-constant expression and may informally be called a runtime expression. Okay. So a constant expression must be must be evaluated at compile time. Okay, I think we will leave that there. There's quite a while to go, and we've just passed the 3-hour mark. So what we'll do is we will leave a note here. Let's do if 0, end if, and that way we can just type in here. We don't need to do comments. We can just do left off at lesson 5.5 constant expressions. So remember, a constant expression means that the sequence means that each part of the expression, i.e. a non-empty sequence of literal constant variables, operators, and function calls, all must be called, all must be evaluated at compile time. Whereas a non-constant expression doesn't have to be evaluated at compile time and is also known as a runtime expression. Yeah, runtime expression. Okay. So day 9, part 2. What did we do today? So we what did we do today? Started off with constants and strings, and the two types being named constants and literal constants. We did that. We did constant. Floating points, the importance of suffixes for data types such as float, and using F to ensure that it does not become a double by default. String literals, magic numbers, numerical system. So we did binary, which I need to learn up on. We did binary, we did hexadecimal, hexadecimal, and we did octal. And decimal. Decimal. And we did digit separators. We did the default C++ library of, what was it, bitset? Bitset, yes. I'll just remove that there, and then that. Then we also did the as if rule and compile time optimization. Optimization. Then we did constant folding. Slash propagation. As well as dead code elimination. Then finally we did compile time. No, we did const variables are easier to compile. Then we did compile time versus runtime evaluation. And then we finished off with constant expressions, where constant expressions run the sequence at compile time. They must be evaluated at compile time, i.e. the constant variables, the expressions, the function calls, etc. and operators and literals. And then the benefits of compile time programming, such as performance, versatility, predictability, and quality. Cool. That will be it for today. Let me just first of all save it before I forget. And the date today is the 6th of August, 2026. Cool. Yeah. Hopefully you follow along. Hopefully you're enjoying learning C++ as much as I am. If you saw something that I did that was wrong, or you felt that I can improve it, please let me know. I always want to improve. So yeah, please like, subscribe, comment as to what you're enjoying, what you're not enjoying, what I can improve. And yeah, comment, like, subscribe, all that good stuff. I will see you in the next one. Goodbye.